So this question looks hard for one reason, and the examiner expects you to make this one single mistake. Before we answer that question, let's do a short introduction to electrostatics. So electrostatics is the study of electric charges at rest. Now, electric charge is a property of matter just like mass. There are two kinds of charges. We have the positive charge and the negative charge. So the fundamental rule is like charges repel and unlike charges attract. So in this diagram, we have an arrangement of particles on a right angled triangle with a particle on each corner of the triangle. So we have the first charge, the second charge, and the third charge. So these are particles on each corner, and it said that the distance between Q1 and Q2 is 5 centimeters. So now Q2 is -2 microcoulomb, Q1 is a +1 microcoulomb, and Q3 is a +3 microcoulomb. So from the information given, let's assign the polarity to each charge. So Q2 is a negative particle, so this is going to be negative. And Q3 is a positive, so this is a plus. Q1 is also a positive, so this is a plus also. So now we know that unlike charges attract each other. So there's a distance between Q1 and Q2, the distance of 5 centimeters, and Q1 is positive, Q2 is negative, so there is an attraction force on this side. And then Q1, Q3, those are both positive, so like charges repel each other, so there is a repulsive force right here. And this one is negative, this one is positive, so there is an attractive force on this end. So we've been given the distance between Q1 and Q2, but not the distance for these other two sides. So now the first thing we're going to have to do is find the distance for these other two sides, and as you can see, this is a right angled triangle. So for trigonometry, we all know that we solve a problem like this where you have been given only one side and then two sides are missing. So you use Pythagoras theorem, which is a squared plus b squared is equal to c squared. So we only have a, so before we find the other sides, we have to have at least two sides. So we're going to use sine theta. So sine theta, this is the opposite divided by the hypotenuse. So sine theta, and I forgot to mention there was an angle right here which is 30 degrees. So sine theta, so we have sine 30 degrees, and the opposite is going to be our 5 centimeters, and then our hypotenuse, we don't have it. So sine 30, this is half, or 0.5, which is equal to 5 over h. And then your h is going to be equal to 10 centimeters. So the distance between Q1 and Q3, this is the hypotenuse side, so this is 10 centimeters. So now that you have two sides, you can use the Pythagoras theorem to find the other side. So we have a squared plus b squared is equal to c squared. So our a, that's 5 squared plus b, and our c, that's 10. So our 5 squared, that's 25, plus b squared, that's 100. And then we're going to have, that's 100 minus 25, that's 75. 75 is equal to b squared, then we square root. So now our b, this becomes 8.7 centimeters. And just like that, we have the distance for each side. So that's 10 centimeters right there, and that's 8.7 centimeters. Now remember, these figures are the distance between the charges. So distance is always measured in meters, so you have to convert them. So you have to start, we know that 1 meter is equal to 100 centimeters. So for your 5, you're going to have to divide by 100. That's 0.05 meters. And for your 8.7, that's going to be 0.087 meters. And for your the other one, that's 10 divided by 100, that's 0.1 meters. So these are the distances between the charges in meters. Those are the ones that you get to use in your formula. So now let's analyze the forces acting on each charge. So we have an attraction force this side, and this is also an attractive force, so it's coming this side. And then we have a repulsive force pushing these two charges apart like this. So now let's say maybe you asked the question to say find the net charge, find the net force acting on Q3. So this is Q3, and when you hear the words net charge, or net force, this is just another way of saying all forces acting on something. So the net forces acting on Q3, it's just a way of saying you have to find all the forces that are acting on this particle right here, this charge. So we have an attraction force acting in this way, then we have a repulsive force coming down this way. So there are two forces acting on this charge. So we have two forces, and you only have to find the net force by adding the forces that you have. But now the rule is you only add forces acting in the same direction, and these two forces are not acting in the same direction. So therefore you resolve these forces into components, into the positive components and the negative components, and then you use vectors to add properly these forces. Okay, let's have a look at the question now. So the question reads, 3 point charges are located at the corners of a right-angled triangle as shown in the figure below, where Q1 is equal to Q3, which is equal to a positive 5 microcoulomb. Now Q2 is equal to a negative 2 microcoulomb, and A is equal to 0.1 meters. Find the resultant force exerted on Q3. Okay, so we have an arrangement of particles again in a right-angled triangle, with each particle resting on each corner. So now the distance between Q2 and Q3, that's A, and our A is 0.1 meters, and the distance between Q1 and Q3, that's the square root of 2 multiplied by A, multiplied by 0.1. So we have our Q1, which is equal to a positive 5 microcoulomb, and our Q3 is the same, it's also a positive 5 microcoulomb. Our Q2, that's a negative 2 microcoulomb. So our Q1, that's positive. Our Q3 is also positive. Our Q2, that's the negative we have. So now the forces acting between these particles, so we have a negative and a positive on top. So this is an attraction force in this direction, an attractive force. Now Q1 and Q3, those are like charges, so they are going to repel. So a repulsive force going this way, also pushing this charge the other way. But these two, they are attracted to each other, so they come close. So those are the forces. So now the question says we have to find the resultant force exerted on Q3. So the resultant force is just the same as the net force. So we have to find now the force, the relationship of how these forces push this, and we're going to have to add these forces. So we have an attraction force and a repulsive force acting on Q3. So to find the magnitude of those two forces, we use Coulombs law, which says the magnitude of electrostatic force between two stationary point charges is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. So this is F. F is equal to the constant K, that's maybe charge A multiplied by charge B, and then divided by the squared distance, the R squared, the distance between them. So that's what you use to find the forces, these two forces. That's the formula you use. So let's find the force, the attractive force between Q2 and Q3. So the electrostatic force between Q2 and Q3, we're going to call this force 2-3. So it's going to be force 2-3. So it's equal to the constant K, that's Q2 multiplied by Q3, divided by the distance between them is A. So that's A squared. So now the force 2-3, the constant K, that's 9 times 10 to the power 9. And our Q2, so you don't have to indicate the polarity of the charges. Let's say this is Q2 is our negative, so you don't have to say -2 microcoulombs. So you just get the 2, you just get the figure alone. So this is a 2. Now micro, that's 10 to the power -6. So you multiply it by 10 to the power -6. And then our Q3, that's 5 times 10 to the power -6, divided by our A, that's 0.1 squared. So on top we have 0.09, and at the bottom we have 0.01, and then you divide that to get the force between those two charges. That's a 9 Newton force. So the attractive force between Q2 and Q3, that's the 9 Newton force we have there. Now let's find the repulsive force between Q1 and Q3, this one. So we're going to call this force 1-3. So it's the same, we start with the constant, that's 9 times 10 to the power 9 multiplied by our Q3. Our Q3, that's 5 times 10 to the power 6, and our Q1 is also 5 times 10 to the power 6, and the distance between them is the square root of 2 multiplied by A. So that's the square root of 2 multiplied by 0.1, and you have to square this. So our force 1-3, so on top we're going to have 0.225, and at the bottom you're going to have 0.02. and the force between those two charges is 11.25 newtons. So those are the two forces acting on Q3, the attractive force and the repulsive force. So you have the distance between Q2 and Q3 and the distance between Q1 and Q3. So you can find the distance between Q1 and Q2 using the Pythagoras theorem, but the distance between these two is really irrelevant in our solution, so we don't have to find it. So we have the two forces acting, and now we have to find the resultant force of those two forces. So like I said before, you only add forces acting in the same direction. So you have to resolve these two forces now into vector components so that it would be easier for you to find the right thing, the resultant force. So we have a force pushing this away, it's going this way, and a force pulling this in. So we have two forces. We have that repulsive force going this way and this force going that way. So now I'm going to have to draw my compass right here. So that's my compass. And so now you have to find the angle of these forces. So we measure the angle of the force from the positive x-axis going counterclockwise. So if you have a compass like this, so you have to measure the force or the angle this way, counterclockwise. So that's a 90 right there, another 90, that's 180. So that's what exactly we're going to do right here. So this repulsive force cuts the 90 degrees angle exactly in half. So this angle right here is a 45-degree angle. So the angle for this force is a 45-degree angle. And then the force, the attractive force going this way, we have to start again from the positive x-axis, going counterclockwise. So this is going to be a 90 until we meet the force. Now that's going to be 180. So for the x and y components of each force, let's start with the repulsive force. So we're going to call this Fx in the x component. So the force's magnitude is 11.25. So in the x direction, that's cos 45 degrees. And this is equal to 7.95. Now in the y direction, we're going to call this Fy. That's 11.25. Now it's going to be sine 45. It's going to be equal to, once more again, 7.95. So now you come to the attractive force now. So now for Fx in the x direction, you have the magnitude of 9. That's 9 newtons. In the x direction, that's cos. The angle for this force is 180. So that's going to be equal to a negative 9. And in the y direction, you have the 9 sine 180. That's going to be a 0. So at this point now, you just add the components in the y direction and the components in the x direction. So adding the forces, adding the components in the x direction. Let's start with the x direction. Let's call this x forces. So adding the components in the x direction, we're going to have a negative 1.05. And adding forces components in the y direction, let's call this y force, we're going to have a 7.95. 0.95. So now that you have the sum of the components in each direction, so now for your resultant force, it's going to be square root the sum in the x direction squared plus the sum in the y direction squared. So that's square root. So in the x direction we have, that's a negative 1.05 squared plus a 7.95 squared, like that. So the square root, inside you have 64.305, and then the square root of that is just 8.02 newtons as your resultant force. So to find the direction of that force, the direction, so that's going to be, for the direction, that's theta is equal to the inverse of tan multiplied by y over x, and then you have found your direction. So this is just theta, that's the inverse of tan. So that's on top, we're going to have 7.95, and at the bottom we're going to have a negative 1.05. Then you work those two out on your calculator, and then you have the direction of this resultant force.